So hi everyone. Today we'll be discussing about how to code out a basic text classification model using Keras and TensorFlow. Let's get started. So first of all, we will be picking up a data set for ourselves. That would be the movie sentiment analysis data set from Kaggle. So basically, it is not a CSV file; it is a zipped TSV file. So what is a TSV file? TSV file is a tabbed separated CSV file. So in CSV we have a comma separated values. In TSV we have tab separated values. So in this case, while reading this particular TSV, we need to mention the delimiter equals to /t that represents a tab. So first of all, you're reading the train and test data sets that are zip files. So first of all, you're using zip file library. Are you reading the train and test data sets and eventually converting it into a CSV sort of format so that we can get a data frame out of it using train.open train.tsv because it is a zipped version as you can see above, comma delimiter equals to /t because it is a tsv file as I told you earlier, and using pandas.read csv we will be converting this into a data frame. Now looking at the data set, basically you can see four values: phase id, sentence id, phrase, and sentiment. So basically sentiment is the multi-class that we will trying to predict that ranges from 1 to 5. Apart from that, phrases text as you can see. Phrase id and sentence id we won't be using much, but for your reference, phrases are basically small sentence segments that are taken from the same sentence, that are taken from a sentence. So basically as you can see here that we have unique phrase ids but sentence ids remain the same, that is from the first sentence we are getting multiple phrases out of it. That is the whole concept, but we won't be using this concept, so we would be more interested in the phrase and the sentiment of the phrase, that is 1 to 5. Now, I won't be doing any EDA for now because we are more interested towards building out a basic model. So we will be moving on with the pre-processing part alongside the modeling part. So the first pre-processing step that we will be taking is normalization. So normalization in general terms means bringing everything to a canonical, that is a standard form. So like for example, I am a hero. So here you can see that one is capital letter and others are small letters, to bringing everything to small letters. I am, or making everything capital letter. So basically bringing everything to a same standard format. So basic in normalization we majorly have two things: text normalization, bringing the entire text into a canonical format. Now this may include removing digits, removing punctuation marks, etc. Word normalization, converting each word into its standard format. So for example, we have tenses attached with each word: dancing, danced, dances, etc. Though they are from the same family. So in word normalization we will be bringing all these words to dance, so bringing these words into their canonical form. So there are two basic steps that we would be following. Why normalization is required? Because we wished our model not to get confused with too many inputs. Because if like it sees dancing and dance as two different words, it will generate a different mapping for each of them, which is not correct. So we wish to, we are trying to reduce the complexity for the model so that it is able to make sense. Because the crux of the idea remains, the crux of the word remains the same if we are reducing it to a canonical format. So that's the whole idea, to reduce complexity. So the first of all, we will be reducing each phase to a lowercase first. So every sentence would get converted to lowercase now. So every word, even the first letter, it will get converted to lowercase. Second, we would be removing punctuations as well. If you wish to skip that, you can skip that. And remember that we are doing this for both test and train and data set. As you can see, X and Y. So Y is the test data set and X is the train data set. So using regex.sub substitute function basically helps us to substitute values in a particular string. So using this particular pattern, here you can see square brackets /w/s. Using this pattern we would be eliminating all the punctuation mark extra spaces in the data set. Now this is the final output that we get after lowercasing everything and then removing extra spaces, punctuation marks. Here you can see the impact. Now next we'll be moving on to word normalization. So word normalization can be done using two ways, that is stemming and lemmatization. So stemming basically is a rule based method which removes certain prefixes or even suffixes as well, to bring it to canonical form. For example, if you have dancing, dance, dance, so it will try to remove ing from dancing, making it dance, or ticked. If you have ticked, so it might remove ed. So these are rule-based methods basically. Lemmatizer is more of an intelligent system that uses some internal dictionary to convert systems into the actual format that as in the dictionary. Now the case is that lemmatization at times take a lot of time, right? So we would be skipping lemmatization and we would be just doing the stemming part. Though if you have enough time, you can go for both. So using NLTK package nltk.stem, we would be importing Porter stemmer and then stemming each word present in each of the phrase. Now here you can see that how stemming has worked for us. So here you can see it was demonstrated. So ed has been removed in series, es has been removed. So as told you earlier, it is rule based system. So at times you would be seeing wrong words that are not present in the dictionary, but for the system, but for the model it won't be a big issue. Now the next part is we would be trying to generate certain word embeddings for text. So I will tell you why we are doing this. So it is not a mandatory step, because when we will be training the neural network, so eventually we will be having an embedding layer that does the same thing. But for better initialization of weights, so that convergence happens faster, we will be using some baseline embeddings for us. So embeddings are basically converting text into meaningful numerical vectors. So there are multiple methods to convert this text into numerical vectors. One is one-hot encoding that you must have heard of, but one-hot encoding or label encoding, but they have a very high limitations. That in one-hot encoding, the dimension increases exponentially. Like for example, if you have 2,000 unique words, then you would be having a vector of size 2000 for each word in a text, that making it very long a sequence. Apart from that, one not encoding also not able to incorporate the relationship between words. So it can be the case that like king and queen have very different embeddings, but eventually if you look, so they do are related to each other and should have a closer embedding. So one hot encoding fails on on that perspective as well. So we'll be using Jensen's implementation of word to vec for conversion of text into meaningful embeddings. How does word2vec work? You can refer to my previous videos for that. So basically, here you can see the code snippet. Gensims.models import word2vec. Then we would be making a single corpus for all the sentences present in both test and train data set, and then calling out word2vec on the all the sentences. Size equals to 120. It means that we wish to have an embedding of size 120 for each word. An iteration would be 20. Minimum count equals to one, that any word which has occurred at least once would have an embedding. Now if we set minimum count equals to 5, any word occurring less than that in the whole document will get eliminated. So using word2vec, we would be Gensim models word2vec, we would be generating embeddings for each of these words in for each of the word in these sentences. Now if you look for certain embeddings, here you can see that the shape of the embeddings that have generated is 13,906 into 128. So 128 is the dimension for each word, and 1000 and 13,906 is the total number of words that we have. So this is the whole array, a sample that I have shown to you just for your understanding. Now the next step is to so as of now the word embeddings we won't be using them directly, though we can use it, but as of now we won't be using that because we would be using it for initialization of the weights and the embeddings layer. So first of all, so still the text in a phrase column in a dataset remains the same. So using keras.tokenizer and sequence generator, we would be converting this text sequences into numerical sequences for now. So how we are doing that? We're first calling out a tokenizer from Keras. So basically tokenizer does nothing but splits every word in the sentence as single tokens. So just remember that this word2vec we won't be using directly here, but we would be using as an weight. So we are actually here when we're calling the tokenizer part in the Keras, this particular sentence. So now we would be first tokenizing all the sentences into their unique words. Then we will be fitting on the text, which generates a dictionary representing an integer for each of the word present. So it's more like a label encoding you can take, where you're assigning a numerical value to each of the unique word. Now we'll be converting this text to sequences function. So text to sequences does nothing but it intakes a string that we have in the training data set. Then eventually, using the dictionary that we've generated using tokenizer, it replaces all those words with their integer representatives, right? And now finally we'll be calling out sequence.pat sequences. So as you know, sentences would have different lengths. So for the sake of uniformity, and also like when we'll be feeding into the neural network, we need to have uniform length for each of the vector that we're generating. So some sentences might be having more words, some sentences might be having less words. So for that case, pat sequences is called. So pat sequence will help us to pad zeros in sequences which have lesser number of words. So for example, if you can see here, the first sentence has many words as compared to as compared to the third sentence. So in this case, the third sentence will get padded up with zero value so that it can match up the length of the second sentence. This is the whole idea of padding sequences. The output after text to sequences may look something like this. it is still not padded. You can see that two values are there, multiple values are here, three values are there, two values are, so all the vectors have different lengths. This is because sentences have different length. Now after padding, we can see that we are padding zeros in the starting of the array. This can be done like you can add zeros at the end of the array as well, and not by making padding equals to post. Now finally, we haven't touched our label column as of now, which is 1 2 3 4 5. So using one hot encoding, we would be converting this into a one hot vector that is representation something like this: 1000 was 011. So what we are doing is that we are taking a vector of size of total number of classes. So total number of classes is 5. So eventually we have vector of 5. Now depending upon the value, we are assigning an index to each of the value, and whenever that class is present, we will be making a 1 at that point, and respective all the values are 0. So for example, if 1 has a representation this, 2 has a representation this, 3 has a representation 00100, and so on and so forth. So all this get in the while in training, so the labels 1 2 3 4 will get replaced by one hot encodes. And the loss function that we would be using is sparse categorical cross entropy. uh, in case of categorical cross entropy, so basically, there is a difference between the two, categorical cross entropy and sparse categorical cross entropy. I was just trying to brief that. So both the loss functions can be used for multi-class classification, as we have multiple classes, so it is a multi-class problem. Uh, in case of multi-label problems, we can't use it because sparse categorical cross entropy is basically used when we have just one label and the other values are zero. So so a sparse representation can be done. So but in case of multi-label problems, this won't be the case because we will be having multiple ones and zeros. So in that case, we won't be using sparse categorical cross entropy, and sparse representation of any vector helps us in saving memory. So that is why we are using it. Else you can use categorical cross entropy also, not a big deal. The next part is to divide the whole dataset into training test part using scikit-learn model selection. So first of all, um, we would be converting the sentiment column of the training dataset into categorical class into category, and number of classes mentioned as 5, so that the vector can be generated accordingly for one hot encoding, and then we're making a train test split. Now we would be using TensorFlow 2 library, so we'll be importing the required layers and required models for designing a neural network. So let's understand the neural network now. So first of all, we are declaring a sequential model, and in this sequential model, we are adding up a layer for embedding. As you remember that for weights, we have already calculated word-to-vec vectors. So that vector has been placed as weights for the embedding layer. So embedding layer also helps us in generating embeddings for the words. So we are trying to initialize it in a better way. Now we have called up an LSTM layer, called by a flatten, and after flattening the array, we are again having a dense layer, then dropout, then dense and dropout, and finally a dense with value output 5. So I'm assuming that you have basic understanding of neural networks. If not, so you need to go back and have basic understanding neural networks to understand this whole architecture. Though it's not that complicated. So LSTMs, you need to go and read out how LSTM works. If you already know it, that's great. LSTM stands for long short term memory. So basically, these are sequence model in which you feed in sequences and eventually an output comes out of that sequence. So that's the whole case. The loss function is used as sparse categorical cross entropy, optimizer is random, and metric we are using is accuracy. Now this is the whole architecture. So the embedding 256 comma 128. So 256 is the maximum length of the sentence that you're taking, and 128 is the vector representation of each word in that particular sentence. Then you're using an LSTM layer, flattening the output of the LSTM layer, and then calling dense drop, and finally a dense layer with output level 5 with output 5 we are doing because it is a multi-class problem, so we wish to have probabilities for all the 5 classes. Now finally we'll be setting up a model checkpoint also, and then calling out model.fit for 5 epochs and providing it with the validation data set as well. The training starts here. As you can see that I have some logs also. The training has started, as it takes a lot of time, so I haven't posted the results, but I think the result would also be fine because the dataset isn't that complex, and our neural network should perform okay. You might need to tune it a bit. You might need to test and trial a few things, but the result should be fine.